Started on our online learning. We have 3 units left to cover in the course. The first is equilibrium, the second acid-base reactions, and the third organic chemistry. We'll spend approximately 2 to 3 weeks on each section. The first one being equilibrium involves a discussion of the collision reaction theory. You would have discussed this over the years in each of your science courses, but maybe perhaps without the name. Collision reaction theory simply states, or discusses rather, how a reaction takes place. So we know that when we mix, let's say, vinegar and baking soda, they will react, they will give off a gas, they will form a precipitate, etc., etc. But what is going on behind the scenes? Why does that reaction take place? Whereas other things mix together and we see no changes. So let's start with the collision reaction theory. Here's a video I'd like to share with you. As you can see, it's about 5 minutes in length. Very worthwhile video. Hopefully, you'll be able to see and hear this well from your homes. Okay, so to sum up, in order for a chemical reaction to take place, we have to have the particles collide. But when they collide, they must orientate themselves in such a way to form something new, and they must have had enough energy to make the collision occur. This minimum amount of energy that they need is what's called the activation energy. And again, it's the minimum amount. You can have much more energy and therefore, um, we'll talk about that later, but have extra energy in order to keep the reaction going. You'll note there's a video mentioned at the bottom of this slide. We'll leave that for now. You can come back to that as we progress through the course if you need more information or a better summary. So the collision theory states that molecules, particles are in constant random motion. So kinetic, if you're in physics, you know that kinetic means due to motion. So particles are constantly in motion. As you increase energy, the particles move faster, and you can increase that energy by adding heat. Or again, you can remove that energy by decreasing the temperature, removing heat energy. So the kinetic energy of the particles is directly related to the temperature of the cell, the sample. And it's also important to note when we're talking about temperature here, that that's temperature in Kelvin degrees. So remember, if we have room temperature of 25 degrees Celsius, we add 273 to that, and that will give us our Kelvin equivalent. And again, with those collisions, they have to be such that there's sufficient energy to form something new. There we go. Temperature is in Kelvin, 25 degrees Celsius as an example. Beautiful. Okay. If collisions occur, they don't have enough energy to reorientate themselves, then we don't see any obvious change in the reactants. No reaction has taken place. What can we do to change the rate of a reaction, how quickly it happens or how slowly it happens? We can make it so that the frequency of collisions is altered. So either they're not going to collide as often, or maybe they're going to collide faster. And we can also arrange or affect how many of these collisions are actually effective by reaching that activation energy. How can we alter this rate? I'll jump ahead a few slides and show you that we can alter the reactants, we can alter the temperature of the experiment, we can change the concentration, and we can also add what's called a catalyst. In the meantime, though, let's go back and talk about this activation energy. So the energy required for a reaction to take place. Another little video clip here. This one's only 1 minute, but very, very effective. So please focus on. So again, you can see from that very quick video the example here of, let's say, methane burning with oxygen. And as the experimenter and narrator talked, we added heat, we supplied that energy by applying friction using a match and igniting that methane and oxygen. The second example the narrator used was that for lightning, nitrogen and oxygen in the air will do nothing alone, but yet when you add the energy from a bolt of lightning, then yes, they will react with enough energy to cause a reaction. In that case, endothermic, heat taken in. One last little video for you, and we're only going to watch the first minute and a half of this. He again is talking about collision reaction theory and activation energy. Okay, we'll stop there. So again, he was just focusing on the point that you need collisions. They have to have enough energy so that they will reorientate themselves and form something new. The activated complex is a very temporary state. It's the point at which the bonds are broken and new bonds formed, and it's very unstable. So the activated complex in this slide would be this point at the very top of that mountain. The activated complex in this one would again be where my cursor is at the very top of that mountain-like energy diagram. So if we go back to this first energy diagram, we can see this is where the potential energy is of the reactant. We add some energy to it. We reach an activated complex, so that means the reactants are able to collide with enough energy to form something new. They have formed, indeed, some products. Now, what's interesting to note here is that the products are lower in energy than the reactants. So on our y-axis, we see energy. Because the products are lower, that means energy has indeed been lost, and that's called an exothermic reaction. Conversely, in this diagram, this is the one taken, it was a screenshot of the video I showed you about lightning. So we have nitrogen molecules and oxygen molecules not reacting just at this particular energy. However, then a bolt of lightning, added energy comes along, hits them, gives them enough energy to reach this activated complex. The bonds within the oxygen molecules break. The bonds within the oxygen and nitrogen molecules both break. They form NO2 with the energy given to them by the lightning. And in this case, we have what's called an endothermic reaction, because as you can see, the energy of the reactants when compared to the energy of the products, the reactants is lower, so the system has gained energy, and we call that endothermic, as you know from last unit. So products lower in energy, exothermic, products higher in energy, endothermic. And again, as I've already said, if particles collide but they don't have enough energy, the activation energy hasn't been reached, nothing happens. How can we change these chemical reactions? We can change the speed, the rate with which they happen, by altering any one of these variables. What is reaction rate? Reaction rate is the amount of either reactants or products. It's up to you. You can choose. Do you want to look at how quickly the reactants are being used up, or do you want to look at how quickly the products are being made? You look at the amount, the quantity of reactants over time, and then, or look at the amount of products as they form over time. So it's moles per time, amount per time. How can we change that? If we wanted to affect the reaction rate, we could look at concentration. So one way is if we have more particles per volume, there's going to be more collisions. And if there's more collisions, then chances are higher we're going to get new substances formed. They're going to more likely react and therefore increase the reaction rate. We could also look at pressure, but take note, I've highlighted the word gas in a different color, different font, because this only pertains to systems involving gaseous particles. So if you wanted to affect the reaction rate, you could increase the pressure. If you're increasing the pressure, you're decreasing the volume. Therefore, you're making it more concentrated, increasing pressure. So just think of a balloon. If you increase pressure, you're making that balloon smaller. If it's smaller, there's less room for those gas molecules to move. So they're going to hit one another more frequently, and that's going to cause an increase in reaction rate. Temperature, remember I told you with temperature, it has to do directly with kinetic energy. So if you add heat energy, you're increasing the temperature, you're going to increase the reaction rate. I'm just going to move back to this slide for a second and show you at the bottom. Just a 10% increase in temperature can drastically affect the rate of reaction. 10% can double the rate of reaction. So very, very noticeable change there. If you want something to react faster, temperature is definitely one way to do it. Number 4, surface area. And I'm going to do an experiment later this week showing you how if you alter the surface area, you can adjust the reaction rate. So think about if you had a big block of chemical as opposed to little crystals. With a big block, there's not as much surface area exposed. With lots of crystals, there's lots of surface area exposed, and so therefore the chance of collisions is higher. A catalyst is something that you can add to a reaction and it will speed the reaction up, but it is not utilized at all, or consumed rather, in the reaction. So it's a chemical that you add that will help speed things up, and then when the reaction has taken place, you can remove the catalyst and it has not been harmed. So how can we change the reaction rate? Concentration, pressure, temperature, surface area. And then if we wanted to add an additional chemical, we could add what's called a catalyst. If we wanted to slow it down, the opposite of a catalyst is what's called an inhibitor. And that is what we would add, a chemical that we could add to a reaction to slow it down. And like a catalyst, it does not get used up. You actually get the inhibitor back when the reaction has taken place. Okay, just a few diagrams to look at. So this first one, you can see your reactants. Active energy is provided. This is the activated complex. This double-headed arrow vertically shows us the activation energy that was required. If you look at the energy of A, the reactants, compared with the energy of B, the products. Have we gained or lost energy? Is this an exothermic or an endothermic? And of course, you should say exothermic because the energy of products has gone lower than that of the reactants. This particular slide is showing you the energy of reactants, energy of products, and so you can indeed see it's an endothermic reaction. If we were looking at the delta H for the system, which is what we talked about in our first unit, comparing the reactants to the products, this difference right here on the graph is your delta H. So again, this is endothermic because the product energy is higher. This one exothermic, the energy is lower. Comparing the energy of the reactants to that of the products gives us the delta H value, and looking from the reactants to the activated complex, that gives us the activation energy, EA. This one shows you the effect of a catalyst. So without the catalyst, we would follow the blue curve. You can see how it needs a much higher activation energy. When you add a catalyst, it decreases the activation energy. Because you need less activation energy, it's going to take less time for that reaction to take place. So you see both reactions have the same energy in the end, but the one with the catalyst, the red with the catalyst, has a smaller activation energy required and therefore will require less time to get to the product. Reaction mechanism, that's just a series of steps that a reaction goes to. Not all reactions are just one step. Sometimes you have intermediate products formed before you get to your end result. So you might start with A and end up with B, but in between A has changed to B, B has changed to C, and C to D. So those are what we call that is what we call a reaction mechanism, where there's more than one step involved. It could be just one step. It could be as many as hundreds of steps to get to the final product. These are active practice questions. I thought you could just take a look at these graphs, diagram 1 and 2, and then see if you agree with the answers that I have here. So in this particular lesson, we have looked at the KMT, which I'm hoping you realize is kinetic molecular theory. So that pretty much says that everything around us is made of particles. If we want a reaction to take place, these particles that are always moving have to move. They have to hit one another, collide with enough energy to form something new. So that's your kinetic molecular theory combined with your collision reaction theory. Activation energy, of course, is the energy required for the reaction to take place. A catalyst is used to speed a reaction up. Conversely, an inhibitor is added if you want to slow the reaction down. Reaction mechanism, of course, is the amount of the series of steps that occurs from your reactants to your final product. Your rate determining step, I did not talk about in our notes specifically, but let's say there were 3 steps to get from reactant A, product D. The rate determining step would be the step that takes the longest. What's making the reaction take as long as it is, what's eating up all your time. That's the rate determining step. So for homework tonight, I'd like you to read section 18.1. All extra pages are posted on Teams, so read that section. It is about 8 pages in length, but not a difficult read. Read those pages and then answer these 5 questions, please. And then tomorrow when we start, I will go over to those answers. I realize the answers are posted in your textbook. I realize that, but I'm really hoping that before you take a peek at the answers, you will indeed try the questions first. Take out your phone, please, and take a screenshot of this slide. This is going to be the homework where the answers are not posted. Instead, we will go over these answers tomorrow, or next class rather. And these, again, as I said, are not posted. Okay, so screenshot this so you can work on these. And then with our next lesson, just give you a sneak peek, I will go over the answers. They are April 14th. So according to my phone, this has been about 26 minutes. So I'm going to ask you to review and read, and then I will probably see you again, rather not the 14th, but the 15th. So I'll see you again on the 15th, and on the 15th, we'll go over to that screenshot slide, and I also hope to show you a video starting our discussion on equilibrium and have a demonstration lab for you to watch.